Okay, then third time's the charm. So I want to finish this up, at least the answer part, and see what all this stuff that we did in the previous video that showed how to set up the problem actually gets us when we go around and do some of the math. I know some of you may be a little rusty on your vector algebra, so this is going to have a lot of vector algebra in it just to keep you happy, all right? So let's see, we want to write down our answer. All right, and we'll call answer ANS. So I'll just start by saying, well, one, we wanted to, our strategy said we wanted to find R01, right? And you can find this on the screenshot that I gave you last time. That's on PhotoBucket at Physics Ranchler. And so when we find that, remember that that vector, right, is the difference between the vector x0 that points towards the object minus the vector that points towards the source, right, from the origin. These two are frame dependent. This is an independent quantity, right? Or not frame dependent, but coordinate system dependent. This one's independent of that. So x0 was r times cosine theta in the x hat direction plus sine theta in the y hat direction. So it's just some point on a circle, right? Because this represents the position of our charge on that torsion spring, which just twists. Okay, and then we subtract off the point or the source, which is just along the x-axis somewhere minus d. Put that together, and we end up with. Let's see, how should I write that? Well, let's write it so that it gives us the correct sort of distances. So let's say it's minus d minus r cosine theta, and I do that because I want to get an idea of which way it's going to point, right? Which way is the direct vector pointing? D is probably greater than r most of the time, and so this is pointing back towards the origin in the x direction, right? And then we have a plus sine theta y hat. We put the source charge in the along the x direction and the object in the first quadrant, so it should be going somewhere upwards, so we're good. All right, so the second thing we said in our strategy that we wanted to do was to find the force itself, right? Because to find the torque, we're going to have to find the force, and to find the angle, the equilibrium angle, we're going to have to find the torque. So to find that, we just use Coulomb's law. F01 is equal to Q0 Q1 over 4 pi epsilon naught. We've got the direction of R01, the direction from the source to the object, over the distance from the source to the object, squared. So there's Coulomb's law, direction, and magnitude. All right, so what we're going to have to do is we're going to have to take that that r hat and use our relationship for the direction. The direction of a vector is equal to the vector itself divided by its own magnitude, right? So that means we're going to have Q0 Q1 over 4 pi epsilon naught R01 over R01 cubed, right? And then we put it all together, and we start using the variables or the values that we had at the beginning, q minus q, and this vector up here. So we have minus q squared over 4 pi epsilon naught. Okay. Our vector here is minus d minus r cosine theta x hat plus sine theta y hat. And then our distance is d minus r cosine theta squared plus r sine theta squared. Should have an r there. R sine theta squared to the three halves. Okay. So that's our force. We can make it a little bit nicer, not too much nicer, but a little bit nicer by canceling these negative signs. So q squared over 4 pi epsilon naught d minus r cosine theta in the x hat direction plus r sine theta in the y hat direction, right? All over this same thing, which is the square of the difference between the x components minus, or don't need the x hat, plus the square of the y components. Okay, so there we go. Looks nice and dandy. We're ready for our torque. We just use the same old torque that we always have. I'm going to use the symbol N for the torque. I may or may not have mentioned that before because that's what the last book did, and I don't remember what this book is going to do when we get to things with torque, but N is as good a symbol as any, especially if we end up having to use taus later on for something else, which I think we might. So N01 is equal to x0, so the location of the point from the axis that it's rotating around, and that axis is going to be around the z-axis itself because it's going to be perpendicular to the x and the y components. So that's that guy, and cross the force on F01. Okay. So that just means we put this same old vector in here, r cosine theta x hat plus r sine theta y hat, cross this guy up here, which is q squared 4 pi epsilon naught, d minus r cosine theta x hat plus r sine theta y hat, all over this d minus r cosine theta squared plus r sine theta squared to the 3 halves. First thing we can do is pull out a bunch of constants, right? So there's an r here, this q squared over 4 pi epsilon naught. So we have q squared r over 4 pi epsilon naught. We don't have to worry about them. Then we look at these guys to do the cross product, which is going to be in the z hat direction. So we have x cross y minus y cross x. So x cross, we also need this thing here. So x cross y is cosine theta times d minus r cosine theta. So we have d cosine theta minus or times sine theta, excuse me, x to y, right? Times r cosine or r sine theta. Okay, I've got that all confused. Excuse me. Okay, so we've got cosine theta times the r sine theta, so it's just r sine theta cosine theta minus sine theta times d minus r cosine theta, and that's all over this denominator again, d minus r cosine theta squared plus r squared sine squared theta to the 3/2. A nice thing happens. This is a minus r cosine theta times sine theta, so this guy and this guy cancel. So we just have minus d sine theta, right? So we end up with the very satisfactory minus q squared over 4 pi epsilon naught. Then we have our fun denominator, d minus r cosine theta squared plus r squared sine squared theta to the 3/2, right? Taking care of the minus sign, we still need the d and the r and the sine theta. So we have d r sine theta. Okay, so we're getting pretty close. 4 we want to approximate. And what I'm going to do is I'm going to say that theta squared is much less than 1. So anytime that a theta squared ends, anytime you have theta squared plus 1, it goes to 0. That means sine theta goes to theta and cosine theta goes to 1. So this approximation makes things nice and simple. Minus q squared minus 4 pi epsilon naught. Let's go ahead and FOIL this out. That's d squared minus or plus r squared minus 2 dr. Okay. Cosine theta, but we just said cosine theta was equal to 1. And then we said up here, this is dr theta, right? And so we can finish that off by saying it's minus q squared over 4 pi epsilon naught. Rd over d minus r cubed, absolute value of that actually, times theta. Okay, we're cruising along. Let's see, what else do we want to do? We want to find the spring torque. So that is going to be the NS, the spring torque. That's pretty simple. That's kappa theta naught minus theta, just like I talked about in class. And then we set that equal to this thing, right? For the stability analysis. So, and then we have stability. So I'll just write that. That's equal to minus q squared over 4 pi epsilon naught, right? Rd, absolute value d minus r cubed theta, okay? And now we want to just solve for theta. So what do we end up with for that? With that, we end up with so this plus that is equal to 0, right? So I screwed that up. All right. So actually, this is equal to plus that. But anyways, we end up with kappa plus q squared over 4 pi epsilon naught Rd over d minus r cubed times theta is equal to kappa theta naught. Everything's looking good, and then we just say, all right, theta is equal to, if we divide through by the kappa, 1 plus q squared over 4 pi epsilon naught times 1 over kappa, which should remind you of what we did in class on Wednesday, times rd times d minus r cubed, and theta naught in the numerator. So that's what we get for our theta. It's a nice linear function, just like I promised. And I will go ahead and put the graphing into another video so that we can just do that all on its lonesome and not worry about anything else. So, 1 second.